How's it going, everyone? Welcome to today's video. For today's topic, we're going to be talking about how to balance chemical equations. Balancing chemical equations is just a means of accounting to kind of help the number of atoms or of a particular element on one side even out and equal the number of elements on another side. And all this shows is that the proportions that molecules, compounds, whatever's participating in a chemical reaction will have to react in a certain way or in a certain proportion or ratio in order for the reaction to go to completion, I guess. So that if you had this much and this much of two different types of substances, when they react, there will be absolutely nothing left, and all that you're left with is what you end up with on your product side. So we're going to look at a few examples today. The first one I wanted to look at was sodium and chlorine when they react to make sodium chloride. If you take a look really quick, we see we have one sodium, two chlorine over here on the reactant side, but we only have one chlorine over here on the product side. And this implies right now that that chlorine atom just disappeared, and we know that that just isn't the case because law of conservation of matter. So here's how we balance this out. First, write the elements down underneath this arrow. There are other ways to do this, but I like to write it down underneath the arrow. Write the number of that particular element that's on each side of the equation. So for sodium, we have 1 over here and 1 over here. For chlorine, we have 2 over here and just 1 over here. So sodium is good right now, but we'll take a look at chlorine because we got too many over here compared to over here. To fix that problem, we add what's called a coefficient. In this space in front of this compound right here of sodium chloride, we have to add an entire another sodium chloride to get that second Cl. We can't just add a 2 right here because that would be creating a completely different compound, something that I don't even think it really exists. When you react sodium and chlorine together, sodium and chlorine gas, you end up with table salt. So what we do is we add the 2 right there to show that when these two react, they're going to have to produce this in this proportions, and that gives us 2 sodium and 2 chlorine. Well, now we just created a problem up here. Well, we keep going. This is called balancing, and it just takes a little bit of back and forth. So we have 2 sodium now over here and only 1 over here. All we do is just add a 2 right there. 2 times 1 gets you 2. We reassess down here. We've got 2 sodiums on each side, 2 chlorines on each side. This chemical equation is now balanced. And what this says is that for every 2 sodium atoms that you react with 1 chlorine gas molecule, you will end up with 2 compounds of sodium chloride. We leave this blank right here just to show that there's only 1. Let's take a look at a few more examples. Okay, another example that we can look at here is the decomposition of water. So when water decomposes, you end up with hydrogen and oxygen gas. First thing we got to do is we got to write the elements that are participating in this reaction. We have hydrogen and oxygen. And if this is all we have over here, then that's all we're going to have over here. And then I'm actually going to write that just a little bit lower so we have more space. And you guys can see that clear. There we go. We have 2 hydrogen over here, 2 hydrogen over here. That's good. We got 1 oxygen over here, but we have 2 over here. So to fix this problem of lacking of oxygen over here compared to over here, we got to add an entire other water molecule. So we'll put a 2 there. Okay, so that gives us now 2 oxygens, but we added a whole nother water molecule, so we got to add more hydrogens as well. 2 times 2 gets us 4 hydrogens now. Reassess everything. Now we have 4 hydrogens on this side, only 2 on this side. Oxygen appears good. So we got to add more hydrogen. We just add a 2 there. 2 times 2 gets us 4. And then we're good. The reason why I added a 2 right there, say maybe we ended up with 6 hydrogen over here compared to 2 over here. I just added 2 because I knew 2 times 2 would equal 4. If I needed to bump this up to 6, I would have added the number right away. That would have got me to equal that. It doesn't have to be so much guess and check. I recommend, if that's not something that you do just super quickly and you don't know whether to add like a 3 or a 4 or whether you should add a 2, then just start going up slowly, add 1, keep checking until you end up reaching it. Let's go ahead and look at a few more examples. Another example that we can take a look at here is the reaction between sodium hydroxide and aluminum. Right? This is actually a very interesting reaction. Be careful if you try and do it at home. Actually, don't do it at home. Sodium hydroxide, first thing we got to do, we got to write everything out. And one thing I wanted to point out here is now we have a polyatomic ion. That is something that is its own entity when it participates in a reaction. You could just write out the individual elements as you go, and it'll still get you to the right answer. But what I like to do when I know we have a polyatomic ion is I like to just include that as all one thing, because these guys are going to these two elements are going to travel together when they participate in the chemical reaction. This hydroxide here is going to combine with the aluminum here as it did, and those are going to travel in the same proportion, so it's okay to include it just like that. And let's see, we have Al right there. Okay, let's count them up here. We got 1 sodium over here, 1 hydroxide, and 1 aluminum. Over here, though, we have 1 sodium, 1 aluminum, and we have 3 hydroxide. So we got to fix the number of hydroxide first. To do that, we find whatever hydroxide is in over here. Remember, we can't just add a 3 there. That doesn't change that. We got to add the number of sodium hydroxides that will get us to equal the number of hydroxides that's necessary. So I'm just going to put a 3 here, because 3 times 1 will get us 3, and then that's good. But we added more sodium, so 3 times 1 gets us 3 as well. And then that's it on that. We just got to reassess. We now have too many sodium on this side compared to over here. Hydroxide is good and aluminum is good, so all we need to fix is sodium, and that works out because the sodium is as a single element over here. So let's go ahead and do that. To get the right number of sodium, we just add a 3. Fix that. And then we're good. That's balanced. Another example that we'll take a look at. Lead nitrate and potassium iodide reacting to form potassium nitrate and lead iodide. First thing we got to do, same thing as all the others. Let's write down all the ions that are going to participate in the reaction. We've got lead here, Pb for plumum, NO3 for nitrate, K for potassium, and I for iodine. Next step, count them all up on each side. We've got 1 here for lead and 1 over here. We've got 2 nitrates, and again I wrote nitrate here because nitrate is its own ion. It's going to travel over here and stay together, so it's okay to do that. We only have 1 over here though. We have 1 potassium over here and 1 over here, and we have 2 iodine to 1 iodine over there. Okay, lead's good, nitrate is not. So in order to fix nitrate, we got to put a 2 there. There's 2 on this side, so we had to add 1 more, and we just added 1 more. So 2 times 1 nitrate. It's not 2 times 3. This is all 1 nitrate. That's right there. So it's 2 times 1 nitrate that's attached to this potassium, and that gets us 2 nitrate. But it also gets us 2 potassium as well. So we'll just keep going down the list. Potassium right here. Now we have 1 potassium on this side, 2 on this side. So we'll go ahead and take a moment and fix that. So to do that, we got to add 1 more over here. 2 times 1 potassium gets us 2 potassium there. But that also gets us 2 iodine. So we got to put 2 iodine right there. And if we take a look, I think that fixed it. We didn't even have to talk about iodine. Kind of fixed it on its own. We got 1 lead on each side, 2 nitrates on each side, 2 potassium on each side, 2 iodine on each side. So that means for every 1 lead nitrate and 2 potassium iodine, we produce 2 compounds of sodium or excuse me, potassium nitrate, and 1 compound of lead iodide. We're going to look at just one more example of that. So we just write down the elements that are participating in this reaction. We have carbon, hydrogen, and oxygen. It's on both sides. Here's what we're going to do. Here, this is kind of a complex balancing equations because we have C and H right here and oxygen right here, but we have oxygen here and here. So when we change one of these, we've got to take that into account, that the oxygen is going to change because of 2 different adding numbers. And I'll go through how to do that. That's why I wanted to save this one for last. So let's count them up. We have 8, 18, and 2. Over here on the reactant side, we have 1, 2, and we have 2, 3 oxygens in total. We are counting all the oxygens over here. So there's a total of 3 oxygens. So we're going to start off just with this first one here. Start off with the first element that you see. Carbon has 8 over here and 1 over here, so we need to add 8 more carbon dioxide molecules in order to get that to 8. So we already know that off the bat, that's what we got to add. So let's go ahead and put in 8 right there. 8 times 1 carbon gets us 8. Now we added 8 CO2 molecules, so we also need to adjust for the total number of oxygen atoms that are going to be over here as well. So 8 times 2 gets us 16 oxygen atoms, plus 1 more gets us 17. Right, 8 times 2 is 16, 17. Okay, right now we've got carbon fixed. Let's just take a look at hydrogen. We've got 18 over here, but we only have 2 over here. So what do we need to add to this to get us to where we need to go in order to get this to balance out? So we have 18 hydrogen, 2 hydrogen over here. So we need a 9. Yes, 9 times 2 gets us 18. So we go 9 here. 9 times 2 gets us 18. But we also added more oxygen as well. So 9 times 1 gets us, well, it's 9 more oxygen. So we have a total of 9 oxygen over here and 16 over here. So we end up with a total of, that's, oh, mental math, that's 25. Yes, 25. Okay, last thing we got to look at here is oxygen. We have 25 oxygen atoms over here and 2 over here. What do we need to put here to get this equal to 25? Now, some of you guys thinking like, how can we have, this is going to have to be, well, 12.5, right? But we can't just add a half of an oxygen molecule. It's got to be whole proportions. We can't just split an oxygen molecule in half and that's how it works, because that's not how it actually works. So when you come into that instance where you have a half right here and everything else is balanced, just double everything. So what we're going to do is we're going to write that 12.5 right there just to show that we have a half, and because we have that half, we just have to double everything. Otherwise, you can go back and forth and try and figure out what you need to do and kind of go work through that struggle, but let's just save us the time. So we're going to double everything so that we can get this to be a whole. So we had 2 now right here. That gives us 16. 2 times 18 gets us 36. We're going to double this, 12.5. to, that will be 25 oxygen atoms. Wow, 2 octane pulls out 25 oxygen atoms out of the air. Anyway, 25 times 2 gets us a total of 50 oxygen. Now, we'll fix carbon over here. Actually, we're just doubling everything, so we don't even need to look at this because we're following my instruction here. Double everything, so we're going to double this to 18. 18 times 2 gets us also 36. Well, that works out perfect, right on. 18 times 1 gets us a total of, now this is a total of 18, but remember we got to count for this, so we're not going to fix oxygen just yet. We got to double this now, so that is 16. 16 times 1 carbon gets us now 16. 16 times 2 oxygen gets us 32 oxygen. So that's going to be 32 oxygen. 30, 42, 2 plus 8 is 10, so that gets us a total of 50. So we got 16, 36, 50 of everything on each side. Boom, we got it. That's exciting. These are frustrating to do, I know, especially if you're working on your first time and this is the task that you're kind of set with. But what this says is for every 2 octane molecules we have, 25 oxygen gas molecules are needed, and they will produce water and CO2. 18 molecules of water and 16 molecules of CO2 in these proportions. Thanks for watching today's video, guys. I hope you found this helpful. If it was, leave a like, subscribe. I'll be posting more content related to chemistry, biology, and physics in the future. And hope you all have a good day.